Happy Thursday, everybody. I hope you're doing well. Thanks for coming to class today. We've got a great Parrot Act for you, and I want you to log on. So I'm going to put that in the chat. It's a particularly good one about momentum. It's awesome to start a new topic, and it really does connect into energy too. We're discovering that some things stay the same. There's a good reason for it. There's such a thing as a conserved quantity, and we're just starting to get a taste of why that happens. It turns out there's a really deep reason why that happens. It's anytime there's a symmetry, anytime you notice that something stays the same in nature, there's a conserved quantity that goes along with it. And we're just starting to get a taste of it right now. So if you haven't done this yet, make sure that you fill out your attendance form on the Spear student page. You're going to need a paper and pen for notes. If you want to print out our note sheet, it might save some handwriting for you. Make sure that you ask questions. I'm going to be giving you a lot of questions too, to make sure that you understand almost everything in today's PowerPoint. At the very end, there's some cool things I want to stick on just for fun to show you how everything's all connected. Our icebreaker of the day is, what is your favorite type of candy or Valentine's Day sweet? And then the original one that I thought of, but I thought it'd be too wacky, was, can STEM be your Valentine? Can physics be your Valentine? Can chemistry? For me, my Valentine growing up, I think, was like playing piano and doing some physics. And it's so funny because you spend so much time with that passion, with that hobby, that it becomes, like kind of like a love-hate relationship sometimes. And some of you might want to answer like maybe computer science is your Valentine or something like that. But what's there for you, that's not really like a physical person, but just something that gives you comfort, can be good to you and also not so good to you at times. Of course, my wonderful wife and I are going to be having a wonderful Valentine's Day, celebrating, hopefully, probably just hanging out on the couch or something like that. So my favorite type of candy, just to kick things off, is or Valentine's Day sweet. I think chocolate, like a nice rich chocolate, not something that's too like watered down or too milky. Like I kind of like that nice pure chocolate. It's really nice because it's just like it's a lot of flavor, and it's kind of bitter too. And I also like Reese's peanut butter cups too. I think that they have like Valentine's Day versions of those, don't they? That might be kind of fun to just grab some peanut butter cups just for fun. Yeah. And I should grab flowers in a card too. I think that would be appropriate. But my physics is my Valentine and always is. And so is, I think, piano. So I'd love to see what you guys wrote. No worries if you just want to say favorite candy, but maybe you might have some passions and okay, I'm getting a kick out of it already. My favorite candy is Twix, especially when it's cold. First, I agree. That's an awesome candy. I completely forgot about Twix. And not all of STEM can be my Valentine. LOL. Only Mr. Physics YouTube content can be my Valentine. Of course, it's so engaging. I hope that you enjoyed the flipping physics guy, because he actually does some awesome videos. My videos are a little bit drier. I need to make them a little bit more exciting like he does. And he's not afraid of having fun and being like making a fool out of himself. And I think that's super important when you do comedy and content and stuff. You just have to be fearless, but he's very respectful too. So okay, so M&Ms, and sure they can. Okay, so there you go. We got filling the love of STEM in all the students' hearts. My favorite candy is probably the mixed chocolate that comes in the heart-shaped boxes. I forgot about that one too. Yes, exactly. Those are cool, and they all have like different flavors, and you can kind of see, and you can pick out the good ones before you give them to somebody. So you take all the good ones, and then you just give them the ones you don't want. That'd be terrible. Don't do that. That'd be very mean. Chinese food, that's awesome. Nice, cool. Airheads, nice. I forgot about that one too. I used to love those. And let me see if I've got closed captioning running. Live transcript, enable. So hopefully you can see the live transcript now. It looks like it's appearing on my screen in a weird place, and I don't see it on the video. Okay, so I need to figure that out. a little bit. But ideally, hopefully everything I say is on the slides too. Airheads, that's nice. Almond Joy or anything with chocolate, no dark chocolate, is awesome. I love Mexican candy. It's so spicy and I enjoy it. That's so cool. Any kind of chocolate except for a chocolate with peanut butter. Oh no, sorry, but STEM could not be my Valentine's. Okay. Chocolate covered strawberries. Ferrero Rocher, no, STEM can't be my Valentine's. Ferrero Rocher, no, just plain old no. Well, thank you so much for sharing that. If you didn't get to put down what your favorite candy is, I'll leave that poll open. And also, hopefully, you'll be spending it doing something to edify your soul, like doing some physics or chemistry as well on Valentine's Day, and not just hanging out with other people. I'm joking, of course. I hope you have a wonderful weekend and have, a very safe weekend too. Please, we want to see you in class. And I won't see you in class on Monday, but Thursday and Wednesday too. And chances are, thank you everybody for doing your homework. That was so awesome to see those notes come in. If you haven't done those notes yet for the asynchronous, get those in ASAP. We want to, as soon as possible, because we want to build on them. And I want to give you more tonight as your asynchronous homework. There's going to be watching 2 more videos. And just to show you where they are and where this material is, we have it not only in PowerPoint form, but you're going to see it as a Google Doc where you get to see all that stuff over there. And today's topic is all about momentum. And the cool title of today's episode of Mr. Physics is The Real MVP. We thought kinetic energy was the MVP, but it turns out there's a real MVP, and its name is momentum. And you already learned from your video last time that you cannot run from momentum. The only way that you can have no momentum is to have velocity 0, where their v is 0. And this is the real MVP, and that should help you remember that equation. And the way to say it in words is linear momentum is the product of mass and velocity. So if you want to print yourself off one of those, or just work with pen and pencil like I usually do. Usually I just use any notebook paper. That's the way in this room and in this house, that's how I learned physics. It was just with a piece of paper and some books. So you don't need anything fancy. But if you do want to have some fun and feel like, having that worksheet just like old class times, help yourself, because I'd love for you to access the content in every and any way that you can. Let's take a look at where this classwork is. Remember, we're in week 21, and we gave you a preview of the What is Power Key. Awesome. We got 4 more other people turning in. That's fantastic. Keep on turning in. And then today's class, the synchronous, all your materials are going to be right here in S35, day 35. And the worksheet over here is a Google Docs this time. I wanted to have it PDF too, but I didn't get a chance to do that too. Plus, keep it simple. You can make it a PDF anyway if you want to, or convert it that way too, or translate it to any language you want to now. Pretty awesome. And with the key, you'll see all our answers are over here. I'm going to be adding some things that aren't on the key, and hopefully I can post my answers sometime if they're neat enough by the end of the day or something. So you can see some of the things that we add on the spot, just as review and for fun, thinking out loud. So the asynchronous, like I was saying, are these videos, and here's where you can find them. We're continuing with asynchronous learning through a video series called Flipping Physics, and this is going to be part 2 of the week 1 video learning. And you can complete this on any paper, but I've also put like a little note sheet for you here too, so you can print that out if you wanted to. And you can sketch it too. You just need a piece of paper. And especially for the second one, look, I just give you the video and then just say notes, put some notes down, and maybe use the back side of it or something like that, or 2 pieces. It should take you about, let's see, the video, the first one is 4.5 minutes. The next one is 8 minutes. So like 12.5 minutes, maybe like 20 minutes to write up the notes too, or something. So budget around there. But feel free to spend more time with it too, because oftentimes with physics, the more time you spend with it, the more you actually start to understand it. It's when we just like look at it for 2 seconds, it doesn't make sense. But the more that we think about it, the more it can make sense. So maybe 20 to 25 minutes on that tonight, or for the weekend if you need to take some extra time on that too. I understand. I want you to enjoy physics and see it as fun, but we've got that impending AP test. So make sure that you're keeping up with your homework and turning your late homework. It'll help you so much. Join me in the presentation. You know, you can also have an alternate version queued up too. So if you need to, you can be skipping around. But let's get started with the real MVP, worksheet 1. And you're going to see me filling it out too with you. So it will be good. So thanks everybody for coming to class. I really appreciate it. Momentum is a huge topic in physics, and I wanted to get these big topics out there so we can start to play with them until the AP test. So you're going to see us come back to energy, and we hopefully will even get to do some right now. So chances are you already have some ideas about momentum. We just had our the Super Bowl game, and you probably, you know, were thinking about momentum, or they might have even said the word momentum as like two players were like running into each other or something like that, or the ball being caught or something. They always talk about momentum, one player's momentum knocking into the others. But what do we exactly mean by that term momentum? You probably already have some ideas. So for example, you probably are going to get the right answer if I ask you which one has more momentum, a train moving at 55 miles per hour or a car moving at 55 miles per hour, and explain why in maybe like one or two words. Like there's one thing that differs between those two. What's that important word? That's the difference between those two ideas. If you're not sure, let's go get some hints on the Pear Deck. It's pretty cool. Let's see if people have responded. Maybe people are still responding. Chocolate like Hershey's. Okay, so I think we are. Oh, okay. Oh no, that's fine. Yes, exactly. If you are responding to that, but neat. Thank you. Chocolate Hershey's. Exactly. The train has greater mass. The train because it has more mass. The train because it has larger mass. Exactly. Exactly. That's awesome. And feel free to stick in candy too to make this more fun to each slide and see if you can't name a candy each time, a Valentine's Day candy or something Valentine's Day themed, to make this a little bit more exciting as well. But you, everybody's getting the right idea. The way we keyed it up on the answer key that you're going to see if you want to kind of skip to the chase is the train, it has more mass. And you're going to see me write it in like slightly different ways because each time I want to say it and challenge myself to say it in a different way. So the train, and I want to say more mass, basically. Mass greater. And so what would have more momentum? Let's get this next one here. I should have put that one up there too, to give people a little bit more time to respond. Same question. It looks like everybody's been doing their homework fantastically. What would have more momentum? A car moving at 10 meters per second, or say that exact same car moving at 30 meters per second? Which one would have more momentum, and explain why? I'll try to think of another candy that I enjoy. I always did like this is Easter though. I'm just thinking Easter, like Cadbury eggs. That's not Valentine's Day. Anyway, what would have more momentum? We're asking the car or same car, but just that's the difference. Okay, so let's see what our hints are. If you don't know the answer for this one, let's see some hints. The car, when it moves at 30 meters per second, because it has a larger velocity. Exactly. The car moving at 30 meters per second because it moves way faster. Exactly. That's the whole point. Nice job boiling it down to the essentials. It's really important to practice writing physics. The 30 meters per second car because it has a higher velocity. Exactly. Exactly. That's fantastic. That's exactly what we're looking for. Higher velocity. Exactly. So I'm going to say the fast car. And I'm going to say bigger V, or greater velocity, greater speed. And good job if you use that word velocity to give yourself extra bonus points for sticking that word in. And as you see, there's different ways to express this answer. And let's see how we keyed up on the answer key just to kind of give you something to land on. Okay, moving at 30 meters per second because it's going faster. Okay, so fantastic. If you saw the insight that's going on there. And just to round it out, describe a case where a train could have less momentum than a car. So isn't there a situation where even though a train's really big, in other words, big mass, it could have less momentum than even like a little tiny car. Let's say it's like one of the smart cars or like the Prius or something. Nothing compared to a train, in other words. But there's a way that the train could have less momentum than the car, isn't there? Let's give people a little bit of time to respond there. Action-packed Pear Deck. If you missed the Pear Deck link, it's up in the corner. And then here is just the clickable one. Sticking that in chat. And join us. And some of us are getting, I'm going to get some hints from my students over here to see what their point. The train is at rest. Exactly. The train at a complete stop versus say a car moving at 10 meters per second. The car isn't moving. So if the no momentum, if the car's not moving, if it were stopped, exactly. If it was stopped, fantastic. So exactly. So we could say train stopped. And maybe I might want to put down like V equals 0 or something. Car moving. So actually, anytime the car is moving, right? So good job, people who pointed that out. You added some insight to it to really understand what is at the crux, what the heart of this whole thing. So let's see how we keyed it up. The train isn't moving, but the car is. Exactly. Why? Because that V equals 0. So when we're writing a physics explanation, we want to use those types of content vocabulary and that type of wording to do that. Join me writing this up. First, on the key, it says that they have, for this one, it's mass and motion, how much stuff is moving and how fast it's moving. I also want to add just a little bit, one more thing to it. So join me. If we wanted to define momentum, first, there are some cool links if you want to check those out to learn more about momentum. But if we wanted to define it, maybe one way we could define it, and there's many ways we could define it, maybe one way would be mass in motion. So that's what I'll start off with, mass in motion, okay? And it's basically like how much stuff is moving and how fast it's moving, but also direction it's moving. That's the part that the answer key left out that I want to add in. That direction's super important for this. We do talk about that a little bit later, but let's put it in right now. How much stuff that's like matter, right, is moving, or mass, and how fast. Put your own definition of momentum there too. It is moving, so it becomes your own. And also the direction it's moving. Also direction it moves. So the direction piece, super important. And you might know that momentum depends on two variables, blank and blank, just like kinetic energy. Actually, there's a parallel between kinetic energy, but the equation is slightly different. Rather than 1/2 mv squared, the momentum equation is slightly different, and it has slightly different units too, right? Instead of kilogram meters per second, and then squaring that meters per second to get a joule, it has something that's a little bit different, right? Do you remember it from the video? Let's see if we have any hints. Please type if you have any hints for us on here. I'll tell you that just like kinetic energy, so like K, let me just spell it, like kinetic energy, like kinetic E, it depends on two variables. Feel free to unmute too and help me out here. It's mass, right? How much stuff, and velocity, your speed, and the direction that you're moving, direction being really important. And then let's see if anybody has the equation. No responses yet. What's the equation? Somebody help me out here. Maybe type it in chat. P equals mv. Maybe everybody knows this from doing their homework. And then the units are just like we have for mass, right? Wouldn't we have kg? And for velocity, wouldn't we have meters per second? So let's see. 1 out of 2 response. Thank you so much for responding. Let's see. Nice, exactly. Maybe it's a hard one because you have to type all over the screen. Maybe I just had it as a text question. That's awesome. Exactly. Velocity and speed, but we want to remember mass too a little bit. And we have another response. Darn. Let's see if anybody, mass and, okay, so we're getting there too. Those are always hard drawn on the screen too, especially if we're on a Chromebook, so I understand. Linear momentum is a product of mass times velocity. Remember, we might be studying about things that go in circles really soon, so we're gonna have another type of momentum, but linear momentum is a product of mass times velocity. So that's where that PMV comes in. And if you spell it backwards, it spells MVP, right? I'm just going to add little vectors to the tops of those because momentum and velocity are vector quantities. A little bit too big of arrows there, but okay, so momentum is directly proportional to the object's mass and also its velocity. Greater mass or greater velocity, well, that means greater momentum. And momentum, that P with the vector arrow over it, is a vector that has the exact same direction as velocity. So if your velocity is right or up, that means positive velocity and positive momentum with the plus sign. And a negative sign goes with things that are moving left or down. Why? Because that means negative velocity and negative momentum. That's just the way we defined it. We said left is negative, right is positive. So we have to kind of stick to that. And then the SI unit for momentum is kilograms times meters per second. That's kind of like that momentum unit. And the way I write units is I put them in those brackets. And where you get that from, the mass, the M, has the kilograms, and the meters per second comes from the velocity. That's on the shared screen. Before we move on, any questions about some of those things that you might have seen or in the videos and we're going to play with? Let me know in chat. And hopefully your answer key looks a little something like that as you're keying it up. What do we mean when we say momentum is a vector quantity? Remember, there were two types of things, scalars and vectors. And vectors have something really important. So momentum is a vector, but something like KE, kinetic energy, is scalar. And when we say scalar, that means no direction. But vectors are different. What do vectors have? Let's see if we have anybody typing it. Thank you so much for raising your hand and type. Momentum is a vector. Yes, exactly. Here, I'll give you a little bit more time because we might need your help. If you are out there, we need your help. Why is momentum a vector? What does it have about it that makes it a vector? This you might be overthinking this question too. And feel free to check your answer on the next slide as well. Nice. Let's see if we've got anybody helping. Magnitude and direction. Exactly. It gives us direction. Exactly. That is the thing. But that vector, exactly. Fantastic. So momentum has direction. Vectors have direction. I'm just going to say direction. Has direction. Which means that it could be moving left or moving right. Left / right. Or up or down or something like that. And it depends on the motion. It has direction left, right from velocity. So whatever direction velocity has, momentum has as well. And let's see how we keyed it up on the answer key. Thank you so much for helping me key this up. I appreciate the activity and the engagement. It has magnitude and direction. Okay, so it has direction, and maybe we should stick that one word, magnitude. Nitude. Has direction, has magnitude, and has direction. There we go. Magnitude, remember, that's just a fancy word that means size or amount of something. So it has size, how much of it, and it also has direction. Where is it headed? If there's a lot of it, has big magnitude, and it could be coming in from the left or the right or the northeast. Suppose a 2,000 kilogram train, okay, is traveling west at 10 meters per second. Okay, list 2 ways the train's momentum could change. Here, I might need some help with this one too. Remember, all vectors have magnitude and direction. So the train is going to be able to change its magnitude how, and how is it going to be able to change its direction? What are some better words for that? And like more descriptive words for what the train would be doing. And feel free to type in chat or unmute too if you want to. We might need some help with this one though. The hint is it has magnitude and direction. So how could the train actually change those two things? What would it do to change it? And that we do have hints on the presentation if you want to. I'd love to cold call people too. It'd be cool. The train could, okay, I'm gonna give you a little bit more time. Thank you so much for formulating it. Are there any of my physics rock stars out there who would love to unmute and let us know, or type it in to let us know? Thank you. Let's see. What's nice about this pear deck is it's anonymous, so we don't know. Could drop off some luggage, some weight. That's awesome. See, look at that. This is brilliant. You're on the right track. It's exactly change in velocity or change in mass. Exactly. That's what we're getting to. I forgot about the mass thing because remember, momentum has mass. So it's a good thing I did ask everybody. Velocity change, exactly. Change in momentum, change in momentum. Okay, so I like that luggage thing. Okay, so that's that change in mass too. Write down that luggage. That was really creative. Change in mass, change in momentum, exactly. Velocity change, exactly. Okay, so we've got 2 ways we can change. We can change m, and that means mass. Maybe I'll write out the word just so it's not cryptic. Change mass, and that means like drop off some luggage. Exactly. That's awesome. I'm totally writing that one down. Exactly. Way to get creative. Change mass, like drop luggage or add passengers, right? Passengers too, if you feel free to take that one. Passengers. Thanks for filling this out with me, everybody. Change in mass, change in momentum, change V. Okay, so changing V, changing velocity, well, close enough. Kind of looks like it was spelled in Mickey Mouse font. That's where things started to go wrong. Okay, velocity, that means speed, right? So speed up or slow down. Or also somebody also said, did somebody say, or okay, change tracks to switch directions. Exactly, brilliant. Okay, so change tracks, change direction, that's like change tracks. Or go the other way on the track. Brilliant. Okay, that's fantastic. I think that's the best that's ever been filled out, except for my handwriting. But it's in terms of the content, the quality of the answers and everything. That's awesome. Introduce more air resistance. Exactly. So there could be an opposing force. There could be exactly from air resistance slowing the train down. Exactly. So introduce a force, we could also say. See, that's brilliant. Here, where do I fit that? I'm going to put that in the margins over here. Teachers love it when you write in the margins, and don't they? Okay, so we could also have air resistance. Air resistance. I'm just going to maybe put air resist. So external force, external force, something like that. Great, nice thoughts. Brilliant job, everybody. So what does it mean to say that momentum is a vector quantity? That means it has magnitude and direction. How could we change the train's momentum? We could be going faster or slower, or we could add or remove mass. I like our answers better. That's what's so cool about filling this out with you in real time. But those are definitely the right answers. So if you take those, if we didn't put enough of our stuff in there from the answer key, put them. Add or remove mass might be a good thing to put down. Okay, so while momentum is interesting, we're more interested in change in momentum, and usually that's when the cool stuff happens, like collisions and when stuff slows down or speeds up because of forces. Let's write an equation below for a change in momentum. So we're going to be using, remember, the delta symbol for change in and P for momentum. You remember from watching the video, why we use P for momentum. If you didn't see that video, check that one out. It's very wacky. And then let's write down, remember, a change in momentum means final momentum minus initial momentum. And so it's like mass final and velocity final. So we multiply the final mass of something, because remember, something's mass could change. The train could drop some luggage or passengers off, or there could be air resistance that changes its velocity. So, or its mass, maybe there could be so much air that it knocks something off. Who knows? But the mass could change of this train, maybe even grinding its wheels on the track. So for objects that mass changes, we have to keep track of their final velocity and compare it to the product of initial velocity times initial mass. Mass initial times velocity initial. And so we multiply those two numbers together. We're going to be doing that later in the problem set. And let me know if you have any questions about this. But everybody's doing such an awesome job on that. Hopefully, I think we're good. Let's instead practice on this and using this equation. And you'll see this equation pop up a bunch of times. Oops. Let me take away my answers from last period. Oops, darn. Still has some stuff on it. So let's take a look. If we were to determine the momentum of a 60 kilogram halfback moving at 9, what would we get for the answer, or the math that would go along with it too? Somebody could help us out with that in chat too. And remember, we're just applying the momentum equation. So remember, we're starting with P equals M times V. And we have to consider direction. Direction's important. Sometimes it's going to be a positive velocity. Sometimes it's going to be a negative velocity. Keep making those arrows a little bit too big here, just so you don't end up doing that in college, making these huge arrows, little tiny arrows. Momentum is just M times V, so let's do a couple of those calculations. See the chat. Okay, nice, exactly. So this is the way we do it. Perfect, exactly. But remember, it's kilograms meters per second squared. So exactly, take that 60 and multiply it by the 9. Exactly. Remember, this is not joules. Unfortunately, the units for momentum are kilogram meters per second, and 6 times 9 is 54. And if I add a 0 at the end, I get 540. And so that's how I get this guy's initial momentum, or his final momentum. Exactly. Nice job, everybody, for helping each other out. The units, we want a unit for momentum to save us from writing it so many times, but unfortunately, we just don't have one. They haven't invented one yet. Or I think it should be called the Sandoval. I keep on trying to work on that, but they won't accept my calls anymore. Okay, so as you see, we keyed it up just like that, and you want to show your substitution step. That's super important. You want to quote your equation and show that substitution step. Don't just write down 540 unless for a multiple choice where you just need that answer, you know. So for this next one, I'm going to give you a hint. It's just the same way, but that negative is going to play an important part in it. So make sure you remember that in the sign, and let's see if anybody is helping with this. Nice, exactly. So let's join them writing it out together. So the momentum, it looks like, is 1,000 kilograms times that negative 20 for velocity and meters per second. And look at even units and everything. That would be 20, and then we need 1 0 from the 20, and then 3 more zeros from the 1,000. Gives me kilogram meters per second. That negative sign, this negative, that means something's heading left or backwards or down or something. Exactly. Fantastic. Great job, everybody. Let's take a look at this next one too. Okay, so let's do this bullet problem. Try this one out. Now remember, we were just multiplying two numbers, but when we obey the equation, we just can't stick the numbers anywhere. If we're given something with the units of kilogram meters per second, that's its momentum. And now we're given the mass too, and we're asking how fast. That's my question. Fast would be velocity, right? So it looks like now we're given, instead of what we usually have, just multiplying the two numbers together, it looks like they're giving us 1.68 to be put on the left. I can tell by those units. The units really give it away. And then on the right, I want to put a number. It looks like this bullet is 42 grams, right? No, 4 grams, excuse me. And we have to put it in kilograms. So we are solving for V. And when we do, we get the magic number. Let's see if anybody got it. Nice. Nice. Cool. So it does turn out very nice and even. Let's give people a little bit more time too. Thank you for teaching the class. Look at how easy it is. When people do their homework, they can be the teachers. It's awesome. I love it. And also, you might know this from another class too, and your own experience, your own studies in physics. So thank you so much for bringing that knowledge to class today to help us out. And I see 400. That's right. I actually need to solve the problem. 400 meters per second. Fantastic. Nice job, everybody. Okay, so it looks like we've got 400 meters per second on the answer key. We're all right. We should give ourselves a pat on the back. How about this? Velocity were doubled. I actually kind of want to help you out with this one. The answer key says it would double, okay? And I want you to try this next one too. Think about what would happen if it were triple. So the answer is going to be double, but I want to show you how we get that. P doubles. Okay? Let's see how we actually get that. So join with me writing this down. And I'm going to share my different screen just for 2 seconds, just so that people see when I'm writing down. Neato. Okay, so we're starting with the equation momentum equals mass times velocity. And then we're going to make a box for every variable. When something's velocity doubles, but we don't change the mass, we put a 1 in for mass because it didn't change. We're going to keep track of how something changes, not the actual numbers. But there's different ways we could solve this problem. Like if we wanted to, we could just invent a mass. We could say like, what would happen if the mass were like, I don't know, 1,000 kilograms? And believe it or not, we could do the whole problem and then we would get the same answer. But I want to show you a slick way of doing it. When the velocity doubles, it's like I put a 2 in that box for velocity. And what would go in the box for momentum to keep this equation true? Well, you already know the answer. The answer is doubles. But the reason why it doubles is because there's a 2 that goes in that box. This is not the same with kinetic energy. Look at what would happen with kinetic energy. Kinetic energy, if you remember, was equal to 1/2 mv squared. That v squared means that if velocity gets doubled, kinetic energy would go up by 4. So kinetic energy would increase by 4. Kinetic energy would quadruple. Quadruple. K would quadruple. So even though we would think that, oh, anytime we double something, the other thing doubles too. It's like that with momentum, only because both mass and velocity are treated on equal footing without any squaring or any exponents on them. But you see, if we had 4 times the, if we had 2 times the velocity, kinetic energy would actually go up to 4K, and momentum would only be 2 times the amount. It's all because of the way that that velocity is treated. Now, help me out with this next one. What would happen if velocity were tripled? And just as like a little bit of an extension and also a review on kinetic energy, what would happen to kinetic energy too if velocity were tripled as well? Here, let me get you started. Remember, for momentum, it's P equals mv, and we're going to make a box for each of the variables. And for kinetic energy, we do almost the same thing, but there's a slight catch. The number 1/2 never changes. So believe it or not, it doesn't get a box. We're never going to be changing the number 1/2. So when we make a box, we only do it for variables, not for constants. So in other words, that 1/2 goes away. And if we put that 1/2, we don't get the right answer. So, and I can show you why that's the case too in a later class. We did it first hour, and I think people got a kick out of it. So if you want me to show you that, make sure that you type that in chat, and then we can have a little bit of a, I can show you why that works out, why we don't have to do that. But for kinetic energy, what would happen is, well, I guess mass is staying the same, velocity would be tripling. So look, we would have a 9 times the amount of kinetic energy. What would happen with mass and velocity? Let's see with momentum. Let's see if we have any hints. Increased by a factor of 9 times if kinetic, great. Somebody's getting the pattern for kinetic energy, fantastic. And that means we probably know what happens with this too, but just in case, help me write it out here, that we want to put the 1 in for mass and 3 in for velocity. So we get 3, so it would triple. P triples, momentum triples, and kinetic energy, KE, would go up by 9 times. So don't think just because you're always tripling something that something else always triples. It depends on the formula. We have to use that formula, and we have to pay attention to the variables and the exponents. We kind of don't care about the constants in the equation because those never change. So let me see if anybody is saying, please, Mr. Sandoval, show me how the constants don't matter. Okay, cool. Let me know because I can show you, and I just don't, I want to keep on plugging in with these problems, going through with these problems too, and just kind of show you the technique of doing these. So let's try something a little bit different if mass were doubled. And let's also do it for kinetic energy as well. Let me stop my screen share on that screen because I think I still have it in my window. Then I want to project the hints. Okay, neato. Okay, try this one. What would happen if mass were doubled? Let's say by adding more passengers or a greater load, like more cargo or something. Well, one more time, we make a box for every single variable, but not the constants. And we're going to be using just a little algebraic trick called proportional reasoning to see how things change. Let's also do some review for kinetic energy. Remember, kinetic energy was 1/2 mv squared. And since 1/2 doesn't change, it would get like a 1. If it did have a box, its box would be 1 because it can never change. But mass, on the other hand, is going to double. Velocity is going to stay the same. So look, finally, kinetic energy and momentum are doing the same thing. But why? It's because, not because they just said doubled. It's because the equation, when we plugged it in, squared a 1 and didn't really help. Oops. Here, I'll let you help with the next one. I'm going to need your help with the next one. Momentum would double. So that's how we get on the answer key why momentum doubles. Try this last one. If both its velocity were doubled and its mass were doubled, what would I get for that answer? And I will need some help with this. What would happen if I changed 2 things and now there's no 1s written in the boxes anymore? The technique still works. I'd love to see your thoughts on it. I'll give everybody a little bit of time to write that in. Hope you're having a wonderful afternoon. We're going to have a little calculus connection, but I want to make sure we understand everything we need to know about momentum. Okay, let's see. Oops, I was writing on the entire thing, huh? Let's see if we have any hints from some awesome physics students. 4 times momentum, nice. 8 times the kinetic energy. Okay, cool. So that's what we're seeing. Neat. Okay, so let's do some math to show this. 2. Thank you so much for the hints, everybody. That's awesome. Oops. So let's try this one out. And it's both its velocity were doubled and the mass were doubled. So P equals mv, put a 2 in for the mass, put a 2 in for the velocity, and we see that momentum quadruples. Okay, let's do the same thing with kinetic energy, just for fun, because physics is fun. And remember, because the constant never changed, if it did get a box, it would have a 1 in the box because the constant never changes. And anytime something doesn't change, we put a 1 in the box. And so for mass, we're going to put basically a 2. And for velocity, we put 2. And I can't forget to square it. I almost left out that square. Oh, okay, so that's where we get this. This is 4. Okay. And then times the 2 is 8. So confirmed. I agree with what everybody's saying. Thank you for helping me complete this worksheet. Fantastic, everybody. The answers are 4 for momentum. And if we're doing that kinetic energy review too on top of it, we've got 8. Feel free to just concentrate on momentum if you need to just focus on one topic, but it's great to get some review practice in too. Let's go down and see what would happen to the this truck coming to a stop at a stoplight. Very exciting. So all the time, whenever we come to a stop, this calculation is really going to help us. We change our momentum. We're going to be figuring out the amount of momentum change. Let's write down our givens and our unknowns or notate them somehow in the problem so that we can solve this. Okay, so this is going to be important. Remember, that's our mass. And then this over here, it's traveling at 30 meters per second. This is going to be our initial velocity. And we're using the formula that was on the bottom of the first page. And it comes to a stop at a stoplight. Calculate the truck's change of momentum. Okay, so stopping at a stoplight, what velocity are you going if you're stopped? If I could get somebody to unmute or type in the chat or something like that. What velocity are you going if you're stopped? If you're not moving, the truck was going 30 meters per second, but when it stops, what would its speedometer say? Thank you, everybody. Thanks. Awesome. I just wanted to, I know we're juggling like 3 windows at once, probably, or 4 or 5 windows. Thank you. I've got snaps to everybody. Feel free to share it publicly in chat too. I'm just going to give a shout out to an awesome student has given us the answer, and it's 0 meters per second. So in other words, stopped, we just write down 0 for that. Okay, why is that important? We're going to be doing a calculation for change in momentum. Remember, it's final momentum minus initial, not initial minus final. You always go final minus initial. So it's final mass times final velocity minus initial mass times initial velocity. Okay, let's start to substitute in and show our substitutions, not skipping any steps, because the AP people really like to see all our work. So this is where we put the 2500, and we can put the units in there to really show that we know what we're doing. And the 30, oops, almost made that mistake. What did I just almost do wrong? Here, maybe somebody can show me, because the mass I did right. What did I do wrong, or where do the numbers go? Where does the 30 go? Where does the 0 go? And what's the answer then? Feel free to type the answer into, just the answer if you want to, into chat, or if you can show us in a couple steps, Feel free to leave out units if you're just typing really quickly. You can just type, show us the numbers that you're showing. Where does that 30 go and where does that 0 go? I need some help with this. Thanks, everybody. I know somebody's busily typing. So as you see, the 30 goes in for the VI. Ah. So which comes first, the 30 or the 0? The 0. Because we're moving to a final velocity of being stopped. Whenever we go to stopped, 0 is our final velocity. And we start off with 30, and notice how we get that negative sign in there. That's why this negative sign being super important, direction being super important, we always need to keep track of what's final, what's initial, writing down our variables in some way in a table or notating them quickly. Because what we want to see is this object losing its momentum because it's being stopped or it's stopping. Anytime you lose momentum, it's like you had something, like let's say they had positive momentum to begin with, and then because they lost it all, the change of momentum was negative. So that's like they're losing momentum, losing motion, and they're losing it to the left side, it looks like, the negative side. So my change of momentum is actually a negative number because I had positive momentum and then I had 0 momentum. Why 0 momentum? Well, you can't, as you know from the video, you can't run from momentum. Whenever an object has 0 velocity, it has 0 momentum. Nice job. Okay, let's see. The same truck is now starting at, let's say, 30 meters per second, and it increases its momentum to 84,250 kilograms. How fast is that truck going now? So the truck is starting at 30, but it's increasing it to momentum 2. Okay, so that means that this is the final momentum over here. How fast is the truck going now? That's like its final velocity. It's the same truck. We need to use the mass from before. Okay, so in other words, final momentum equals final mass times final velocity, or just momentum equals m times v. We're using it in the same way. The 84,250, here, let me see if I have any help. Oh, no response. I think everybody's busily writing, and it's hard to write in 2 places at once, but thank you for making this class really engaged and active. You really did make this a fun class. Mass is the same as it was before, 2,500. And maybe we can stick on some kilograms in there, put some kilograms. That makes it look like it's dividing kilograms, though. kg. And then multiply that times velocity, which we don't know. So leave that as a VF. And then what do we get if we solve for final velocity? Anybody? No worries. Everybody's hand's probably exhausted. For final velocity, we've got 84,250 kilogram meters per second. Oops. No, that's not right at all. That's the momentum. But when we put that into our calculator and we divide the 84,000 by the 2.5 thousand, then we get 33.7 meters per second. So that's how we solve for our unknown final velocity. Now it's known. Okay, I want to make sure that if anybody had any questions about that, they get to ask it and feel like they really understood everything in physics class, like 100%. So are any questions out there, or any other thing that anybody's thinking of? Hopefully everybody's doing awesome today. Okay, these next slides are just for fun. Okay, they're very calculus heavy. So no worries if you, like, by the end of it, your head hurts a little bit or something like that, because these are attempting to show you that calculus is going to help us get some discoveries in physics and help us think about physics. So I'm going to kind of switch my screen here a little bit and screencast so I can write on the PowerPoint presentation. Here we go. Okay, so these next slides are just for fun. They're going to tell you how to get the equations, but the test is going to be mostly, your AP test is going to be mostly using the equation. So for the most part, these will just be equations on an equation sheet. However, I wanted you to see some of this in high school to see how this is happening. And look, we get to use calculus. So I'm going to need active engagement on this one. Ask questions in the chat, please, or unmute, because I need your help unpacking this concept. You guys know about the derivative. Students know about the derivative now from calculus. They know it's like a rate of change. What if I were to tell you that there's a connection between momentum and Newton's second law? Newton's second law was F equals ma. F net equals the sum of the forces, remember, equals mass times acceleration. There's a calculus connection. And so here's what we're going to do. We're going to take that expression for momentum and we're going to differentiate it. What? That's crazy, right? No, we can do that. We can take how fast something changes in time and do that to any function we want to. So if we had a function describing momentum and the function was equal to the function for mass times the function for velocity, we could take the derivative of both sides, that is not ddx, but we're going to take it with respect to time to see how fast momentum is changing. We'll take the derivative ddt of both sides with respect to time. When we take a derivative with respect to time, we're asking how fast is something changing? So on the left, we're going to be asking how fast is momentum changing? Remember, we're just taking the derivative of both sides. And when we take the derivative of the left side, we get dp dt, which is the rate of change of momentum in time, how fast momentum is changing. We call it the first derivative with respect to time of momentum sometimes. But the right side is a little bit more complicated, isn't it? Because it looks like it is having two terms. And so if mass isn't constant, if it's changing is not constant, we have to use a product rule on this. And who out there remembers the product rule? You remember that you differentiate the first term and just kind of leave that second term alone. And then there's another term where you differentiate the second term. So that's what we're going to do. We're going to break apart that product, we're going to break apart the derivative of a product into two parts. The derivative of the first term times the product of the second term. And the first term just kind of stuck out in front, is almost like treated like a constant for the minute. And then the derivative of the second term. I'm going to pause right there. What did we do? Why are we doing it? We're going to find out how fast momentum changes. To find out how fast something changes, we take the derivative. When we take the derivative of the right side, we have to use the product rule and break it into two parts. This part represents how fast mass is changing. This part over here represents how fast velocity is changing. Why? Because when we take the product rule, we're breaking things apart to see how each of those terms changes. And that's a really important thing we're going to see travel with us through calculus, through even into higher dimensions, that concept of the product rule. If mass is constant, like let's say for a bouncing rubber ball, where mass never changes, we don't even have to worry about that first term. Mass is not going to change. So it's almost like this rate of change for mass is zero. But for other things, like when a planet crashes into another planet or a car accident, where one part of the car goes somewhere else, the car's mass changes a little bit, or the planet's mass changes a little bit. So we can't just throw away that term. But for something like a rubber ball that just is bouncing on the ground, or something like metal that doesn't cleave, or will stick in one piece, that first term that represents the mass change would just be 0. In other words, we could just stick in 0 for that first term. Or we could have done this an even better way, where if mass is constant, you know that I can just take it and stick it outside of the derivative. Either way, that first term represents when mass changes. And that second term represents when velocity changes. And now you might see an old friend. You remember that there's a way that position and velocity and acceleration all talk together, all work together. It's through derivatives. And you remember that the derivative of velocity with respect to time is something that we have a familiar name for. Does anybody remember what dv dt actually is? For dx dt, that was velocity. But for dv dt, that's something called acceleration. So we see a familiar friend. Whoa, let's back up. I think that there's a lot happening. We're going to take the derivative of momentum. And when we do, if mass is constant, it's like taking the derivative of only velocity. And we know what the derivative of velocity is. It's acceleration. We can replace that second term with acceleration. And so we see that if we take the derivative of momentum, and if mass is constant, we get that the rate of change of momentum, that left side that's been following us around, is equal to mass times acceleration. Remember when we took the derivative, how we replaced the dv dt with an a? And we see that the rate of change of momentum is something called the net force. In other words, this entire time, whenever we've been talking about net force, we've actually been talking about how fast momentum is changing, the rate that's changing. In other words, net force is the rate that momentum changes. That's something special. And we're going to use this a little bit as we head into next class, and you can see a preview of it in the next couple slides. But as you see, calculus just allowed us to connect momentum, specifically how fast it's changing, to net force. And this may remind you of how we were connecting energy to net force. And I want to kind of pause there. If you want to see other hints about what's to come, I put some additional kind of theory slides, but just for fun, remember, these are going to appear as equations on equation sheet where we're going to use them. So don't get too hung up on the derivations. And if you do, make sure that you just enjoy them and take a couple of days to think about them sometimes, or another session to think about it sometimes. But that's where I want to pause right now. And there are some other fun slides afterwards if you want to see those, because I want to make sure that I remind us that we have to take notes on a video series where they actually do talk about, and you have seen a connection between net force and change of momentum, but they said it in a slightly different way. And you're going to be talking about a little bit more of that in today's video, or seeing a little bit more of that, where we're going to see this way of portraying it. Once again, this is just going to be an equation on equation sheet, but we see we can actually get it from math, and that's what we'll be heading into next time. The connection between changing of momentum, forces, and time. There's a deep connection between forces and time, and it turns out they're the ones that change momentum. just like they were the ones that changed energy when they worked through space. So we'll see that soon, but just so everybody's head doesn't hurt too much, let's pause right there. And I would like to show you some of the async work that you're going to get to see. Remember, you don't need any special piece of paper for this. You can do this on any piece of paper, but you're going to see two things. One's a demonstration about area underneath a curve. I wonder if I can just show just a little bit of that. Here,
Good morning. Let's demonstrate
just a little bit.
Is the area under a.
So we're going to be advancing that, and you're going to see this equation that we just left with. You're going to see that a bunch of times and using it a little bit. And then on Monday, or not Monday, excuse me, the next class, Thursday, we'll be doing our little worksheet with it. And you'll actually get to see the area underneath the graph. He's going to drop a ball on a plate that measures the force. And it's going to tease a little bit about the average value theorem from calculus. So there's a lot of cool things in it. Make sure you do that one. That's about 4 minutes long. And then also, have you ever wondered why you have to bend your knees when you land, or why gymnasts always bend their knees when they land? This video is going to show you what happens if you don't bend your knees and why we do it, and compare the amount of force that our legs would feel if we didn't bend our knees. So another fantastic video for asynchronous work. I really want to thank you for coming to class today. Once again, those last slides were for fun. The derivations are important, but for the most part, we're going to be concentrating on using them. So next class, we'll be putting some of those things that we just saw today to actually good use and plugging in some numbers in worksheet 2 for momentum. But until that time, have a wonderful day. Let me know of any questions. You help make the class better when you ask some awesome questions, and I can't wait for what's coming up ahead. Hopefully everybody finished the synchronous work. And if there's a couple other things on it that you need to fill in, that'll be a good thing to fill them in. So have a wonderful rest of the day. Any questions at the end? Say hi to Mr. Notar for me and all your other teachers. Have a wonderful day, everybody. Thank you, Miguel. Thank you, Daniel. Thanks, everybody. Have a wonderful weekend. Be safe. Do some physics. Remember, physics is always there for you. Calculus is always there for you. Computer science and poetry and all those other things. Take care, everybody. I don't want to keep you, but stay if you have any questions or if you'd just like to say hi. That guy's so wacky. I like his videos. Okay, have a wonderful day, everybody. I respect your time. I respect you. So let me know if you need, what I can do to help. If there's anything I can do to help. Also, don't forget office hours Monday morning. Yay! Talk to you soon. Bye.